Consider that we are viewing this object. It's being illuminated by a white light source and the camera is returning these RGB values or tri-stimulus value. Imagine now that the intensity of the white light source is being reduced. What we observe is that the appearance of the object changes, but clearly the color of the object itself cannot change because the color is a material property of the object. An apple is still red even if it's in a dark room. And what we observe is that as the lighting level has been reduced, the tri-stimulus values have changed. They have all become smaller, but the ratio between the tri-stimulus values remains the same. And what we would like to do is to find some way to transform the three tri-stimulus values to one brightness value and perhaps two color values. One way to do this is to transform the RGB values into chromaticity coordinates. And we divide the RGB values by the sum, by the total tri-stimulus. And we end up with these variables, little r, little g, and little b. And it's easy to show that these vary between 0 and 1. It's also easy to show that they sum to 1. Therefore, one of the coordinates is redundant, and typically we consider just the little r and little g value. Consider this worked example similar to things that we've looked at before. White light falling onto a red apple and producing this tri-stimulus value. Now consider that as a cloud in front of the light source, the overall illumination level has been reduced, and the tri-stimulus value now has a different value, smaller tri-stimulus value than we had before. Let's consider a worked example. In the first case, we can compute the chromaticity coordinates little r and little g. For the second case, where there was a cloud in front of the light source, lower overall illumination, we can compute the chromaticity coordinates and we can see that they are the same. And what we've been able to do then is to factor out the effect of intensity and retain just two numbers which provide some representation of color. Let's consider a two-dimensional coordinate system with the axes little r and little g. This point where r equals 1 and g equals 0 corresponds to pure red. Where r equals 0 and g equals 1 corresponds to pure green, and this point at the origin where r and g are both equal to 0 corresponds to pure blue. It's not possible for a chromaticity coordinate to exist in the space above the blue line, and this comes from the constraint that little r plus little g plus little b has to equal 1. In an earlier lecture, we discussed the concept of gamma encoding. This is where there is a nonlinear transformation between the brightness of the light entering the camera and the magnitude of the signal leaving the camera. Almost all cameras today have gamma encoding in them, and the gamma value is typically around 2.2. What effect does gamma encoding have on chromaticity coordinates? We'll illustrate this with another worked example. We will use the tri-stimulus or RGB values from the earlier example with the full sun and the clouded sun illumination. And the first step is to compute the gamma encoded RGB values, and they are shown here. And we can do this very easily and conveniently using MATLAB. Now let's compute the chromaticity coordinates. In the first case, it's for the full illumination condition, and here are the R and G values. For the second case, with lower illumination, we compute the chromaticity coordinates and we see they are the same as for the first case. So once again, we have factored out the effect of illumination and we're left with two numbers which represent the color. For this case, with gamma encoding, we have factored out the effect of illumination, and that's a good thing. But the actual chromaticity coordinates have a different value to the case we computed earlier without gamma encoding.